start add some details in terms of giving values by which we can measure how good an outcome is. So in the traveling problem, in the getting from A to B problem, we can evaluate our outcomes in terms of, say, distance from our destination. Right, so we know if we look here on the table on the right, we'll see that our destination is B, and the distance from each of these outcomes to our destination, well, if we take the outcome C, which is up here, it may be a distance of 4 kilometers away, and D might be 1 kilometer and E might be 2 kilometers. And now that we have a distance, we can compare outcomes in terms of that distance. Right? So if we, for example, want to minimize the distance from our point at which we disembark, then we might say that C is the worst outcome because it means it's the furthest away, and D is the best outcome because it's the closest. Right, so if we express our preferences in terms of distance from the point of disembarkation, I don't know if that's a word, but of a light. So in terms of where we get off, we can express our preferences by the distance from our outcome or the point where we disembark to our destination. But I want to stress the importance or the difference between an outcome, which was one of the elements we talked about, which is essentially a situation, and the payoff we give, or the value we give to that outcome. So, and this example might highlight what that is. Let's suppose that this road here up Parramatta Road, if you watch my cursor, loops around through this way. So if you choose to catch the bus and the bus ends up going up Parramatta Road, you might get off at C, but you might stay on the bus until it travels all the way around to D. Now, in terms of the distance between the point where you get off and our destination B, going up Parramatta Road has exactly the same distance if we get off here as if we went down if the bus went down Liverpool Road in the first place. Right. So our decision tree, our initial point, we have to choose catch a train. Let's suppose we choose catching the bus, and the bus goes up Parramatta Road. Then we have the choice, once we're here, to get off here or to continue around. Right? So now we're going to say we have a second choice. Right? Our initial choice, which let's say we're looking at the situation where we choose the bus, we have a second choice at that point, which is to alight off at C and walk the rest of the way, or to continue and get off at D. Now, D was the same one as, is the same situation as the one that we would get if we took the bus and it went down Liverpool Road, right? So take the bus, down Liverpool Road gives us to D. And in terms of the distance between these two outcomes and our destination, they're exactly the same. So we might say that they're the same outcome, but it'd probably be better to say that they are different outcomes equivalent in their distance to the destination. And the reason I say that is because while they are certainly, if we're only interested in distance, then certainly they have the same distance, right? Whether we go up this way and get off here, or in the case that the bus goes here, we get off here. But they're not the same outcome because they're not the same world, they're not the same situation. Those two situations are different in terms of the time it took or the travelling time, right? So there are ways we differentiate the two. Now, if we're only interested in terms of if we're only interested in the distance, then we can say they are equivalent, and for all purposes, given our interests, right, in distance, then we may say that they're the same. But strictly speaking, they are different, right? And they are different because there may be an aspect of the problem which we may or may not be of interest to us in this case, which is different. So again, if we measure distances, we can do that as a decision table, and we would put the distance in terms of kilometers. How would we measure distance? Well, there are multiple options. We might also measure the outcomes C, E, and D in terms of traveling times. Now, if this was a loop, obviously, if the bus went up Parramatta Road and all the way here, right, then catching the bus up Parramatta Road would have two possibilities, which was what we looked at earlier. So the reason I wanted to make that distinction is because there is a difference between the outcome, which we're going to look at as an objective situation. An objection may be seen from a third party's perspective or a third person's perspective, and how we think of that outcome. So the way we perceive an outcome is determined by our preferences over these outcomes. So for example, if we play a game of poker, suppose there's two people playing a game of poker, me and you, and I win, then the situation is that I finish with more money than I started, and you end up with less money. I suppose we're gambling against each other. So the situation is the same. It's just for me, I like that situation because I won. Right? If I win, it's a good situation. So I put a high value on that situation and you put a low value. And vice versa, if you win, you would put a high value and I would put a low value. But in a sense, the situation is the same. Right? The situation is one in which one of us walks away with money, more money than we started, and the other doesn't. So the outcome, maybe the best way to think of the outcome is as the independent thing, as the objective event, looked at from a third person's perspective, not necessarily the individuals involved. And that way, different people may see or perceive the different outcome differently. So these values that we put on outcomes are not necessarily part of the structure of the problem. They're now measured by the individuals that are involved, or the decision makers, and different decision makers will have different values. So the element we're introducing now is a way of assigning a value or a preference to an outcome. So in other words, there is some value function that assigns to each outcome some real number, say, which is its value. So now we have, in addition to the previous things we had, which was the structural part of our problem, right? The frame of the problem, which is the elements involved, the structural part, which is the outcome function that maps actions and states to outcomes. Now we're introducing an additional element, which is the values that we place on them. And these values are not inherent parts of the problems, but they're now added to by the individual decision maker. So these are now, this V that we've introduced is a subjective element that goes into our problem. Now we are going to make the assumption, we're going to use the convention in most of our examples that higher values are more preferred. Now, in the examples we saw already, we saw an example where a lower value was preferred. The travel problem, where we wanted to get from A to B, we preferred outcomes that had a lower travelling value. Right? So if we measured in terms of distance from where we disembark our mode of transport to our destination, then we prefer lower values. Right? But in general, we're gonna make the convention, or we're going to follow the convention that higher values mean more preferred outcomes. Right? So we assign more preferred outcomes. Maybe a better way of putting it is we assign more preferred outcomes higher values. So I want to emphasize again that the values that are attached to a problem are subjective. Different decision makers may assign different values according to their preferences for the outcomes. Now there is another thing that we can attach to a problem that is subjective, and that is the information that we have available when we make the decision. In other words, the information we have available about the possible states, the things that might happen, or the sources of uncertainty. So in the travelling problem, this was the bus route, and this might, different people may have different information, right? And based on that, they may make different decisions, right? So, for example, if I have a map of the bus routes, then I may know or have a better idea of which road the bus is going to take. Past experience with this route may also affect how likely I think it is that the bus will go, or maybe with certainty. I might know with certainty that it goes down up Parramatta Road or down Liverpool Road. So we'll call this epistemic state. Don't worry too much about the name. Epistemic just means knowledge, or in this case we're going to talk about information or belief we have about the state of the world when we make a decision. And since these states are things that determine or on which our outcomes are dependent, different people may have different states and therefore may have different views about the outcomes that will, or different beliefs about which outcomes will occur. So we have a number of elements now. We have our action states and outcomes. We also know that the decision maker will add on top of that. So add on top of those structural elements, will add their own personal preferences over those outcomes by deciding which outcomes are good or bad, placing a value on those outcomes, and also, given their state of information, how much information they have, will be able to place or will have some belief on the likelihood of the different possible states, and therefore the different possible outcomes subject to performing an action. So the last thing we want to add, or the next thing we want to add, is the idea of using the structure of the problem based on the elements and the decision tree or decision table, based on the subjective elements of the problem, the preferences which translate into values, and the beliefs which translate into likelihoods of states. Now we want to put all of those together and decide which action should we choose, which strategy, or in other words, which strategy or which choice is the best. And so this is the fundamental problem. And we're not going to go into details today about that, but I just want to give you a feel for what's coming up. And the idea is that we want to make a rational choice amongst the possible actions, given the structure of the problem and given our own subjective preferences over outcomes and beliefs about possible states and their likelihoods. So we're going to describe what we call a process by which we choose. We're going to call that a decision rule. And again, each decision maker will have their own, will follow a different rule based on their own preferences, based on their subjective elements, that is their preferences or values and their beliefs about the likelihoods of the possible states. So the question is, what constitutes a rational decision rule? Right? We want to analyze or make decisions rationally, and we'll talk more about that later. And we want to come up with methods, or what we'll call decision rules, for choosing the possible actions that we have. So coming up, the decision rules we're going to come up with will be determined by the decision problems that will be faced, and we're going to classify this according to the nature of the problem and the complexity of the problem. So we're going to classify the problems that we're going to tackle based on how difficult they are. The ones we're going to look at now are those decisions where there is no uncertainty. We have multiple actions that we can choose from, but the action itself determines the outcome, right? So there is no uncertainty. There isn't multiple possible states. We can assume that there's if you prefer, we can assume that there's only one state, right? And that within that state, the action determines the outcome. Later on, we'll look at the more complex cases, but decisions under certainty is probably the simplest starting point, so we're going to start there. Right, so let's take a look at an example. And this is a software project. Say it could be any project, but let's say the software project, and we've got three possible projects to choose from, A, B, and C, and each one has a different lifetime, right? So associated with each project is a set of say profits over the lifetime of the project, and say project A has a profit of 20 million, which is pretty good. Project B, 13 million, and project C, 17. And the question is, which project would you choose? Notice that there's only really one value for each action, right? So each action determines the outcome, say. Suppose we're only interested in profit and nothing else is relevant in this problem. Okay, so the question is, which project would you choose? Well, I think most of us would choose A, right? It obviously has the highest value in terms of profit. So knowing nothing else, that seems the wise decision. Suppose, though, we break these projects now in terms of their lifetime and the cash flows during those lifetimes. So suppose project A is a 3-year project with a big initial setup costs. So if we look at row A, that represents the choice of project A. In the first year, there's a big initial cost, and then we start making moderate profits in the second, or moderate revenues, I suppose we should say, in the second year, and start making a big income in the final year of the 3. Project B is a short-term, 1-year immediate return profit that makes a reasonable amount in 1 year, and then project C is a 3-year project. We have some initial costs, not as big as project A, but then starts making modest or reasonable profits in years 2 and 3. So we still only have we have the same problem, right? So these add up to 20, 13, and 17. Right, rows A, rows B, and 3, but they're distributed over multiple years. So now you can think that the outcome is the vector consisting of all those years together. That's not good. But it's the 10, 5, and 20, minus 10, 5, and 25 is the outcome, right? So year 1, year 2, year 3, different values year 1, year 2, and year 3. But once we choose A, this is fixed, right? So there's no uncertainty there. We know exactly what we're going to get. What we're going to get is an outcome that consists of cash flows over 3 years. So the question is, which one of those now is preferred? Because there is more to think about, because we have to look at cash flows. But which one is best? Well, if we're only interested in the net cash flow, which gives us the net profit, then maybe we'll stick with A. However, now that we have cash flows, there may be other considerations, like we might maximize the total return. We might try and preserve cash. So, for example, $10,000 debt in the first year is something that potentially could be a problem for some companies. Similarly, any debt, like C, might be an issue. So the question is, which profit would you choose? Now, there are means to take into account cash flows over many years. And these are techniques that are used maybe more so in finance and accounting. This isn't, of course, about finance and accounting, so we're not going to spend a great deal of time, but it is worthwhile maybe having a look at one way of doing, one way in which these things are done. So one of the ways to take into account of the value of cash flows across multiple years is what's called the net present value, which is to evaluate cash flows across at different times in terms of their values now. And what happens is that typically gains or losses later are worth less than those now. And that sort of makes sense, because obviously if I make 13 million in my first year, then I can invest that, like putting it into a bond investment or something like that, to make money, right? So if I'm getting that amount on the third year, I'm losing the opportunity to make, say, for example, interest on it in the first and second year. And so what accountants and people that are interested in finance do is they provide a discount rate, right? So you divide the cash flow over your subsequent years by some discount rate, and the cash flow over 2 years by that discount rate, and then divide it again for each year. So each year gets a discount proportion, and because this is 2 years away, or 2 years in the future, it gets discounted twice. You have the discount, and then that discount gets discounted again. So the general way of calculating net present value over, say, years with cash flows x1, x2, x3 over years 1, 2, and 3, well, the present value is not affected, but future values get discounted, and then future values further in the year get the discounted amount discounted again. Now, if we do those calculations, we see that project A, given the cash flows over different periods, now become 11.5 million in terms of net present value today. Project B, which was an immediate profit, remains unaffected, and project C gets the second and third year discounted by 1.2 and 1.2 squared to give us this amount. So whereas overall we had 20, 13 and 17 as the values or the profits over the 3-year period, in terms of net present value, that 20, 13 and 17 become 11.5, 13 and 17. So you see that for a discount rate, a significant discount rate in this case, which is 20%, which is maybe unrealistic, but that would reduce the value of A, where we're getting profit, where we're making money late in the project. That has significantly been reduced in terms of net present value. Now again, let me emphasize here that there is no uncertainty in this problem, right? Or there is maybe a little bit of uncertainty in how we arrive at a discount rate, which sort of hides some of the uncertainty, but there is essentially no uncertainty in this problem. But there is a little bit of calculation required before we can know exactly the value of each of the possible actions A, B, and C. Let's look at another example, which again is under a problem where we have certainty in our decisions. So in action, certainty in terms of the outcomes and how they relate to our actions. So here we're looking at our fundraiser, right? A school fundraiser, a school community is looking to raise some funds for the school. They have a number of choices in terms of the activities they can use to raise funds. So the two choices are between a fete, where people go and have markets and food stalls and things like that, and a sports day. All right, so if we look here on the left, the two choices are between a sports day and a fete. And if we assume there is no uncertainty, then we really only have one possible state, and that is the actual state of the world, and none of that, no aspect there is going to affect our outcome. So we have, in terms of outcomes, we're going to have little s and little f as the outcome. So uniquely determined by the action, and that is a characteristic of having certainty that the action uniquely determines the outcome, right? Because there is, after all, only one state, only one column. Or we could represent it as a decision tree where we have a decision node here, and that decision node, the action S, gives us a branch that leads to a unique outcome, because there is no uncertainty, there is no branching at a chance node. There are no chance nodes. That is the characteristic of certainty. So in this case we have two actions, sports day and fete, outcomes corresponding to sports day and fete, and we may even really ignore that because there's just one possible state. There is no multiple possible states, in other words, no uncertainty. The question is which action is preferred, F and S? Well, that depends, that is determined by which outcome we prefer, because F directly determines the outcome and S directly determines the outcome. So it's really hard to say which one is preferred unless we have some way of comparing the outcomes, right? So let's suppose that a fete would raise 150 and a sports day would raise 120. Well, then our table looks like this once we introduce our preferences, right? So the values, the value we assign to a fete, in this case, is just determined by the amount of money raised, right? So 120 and 150 for a fete, 120 for a sports day. And if we draw as a decision tree, we see that we get 150 and 120. And this is our value, right? So if we value it in terms of the amount made or the amount raised by the activity, then it's fairly clear that 150 is better than 120. Of course, we might value it in other ways. For example, we might value it in terms of goodwill. Maybe this is somewhere where people really are passionate about their sport, in which case, even though we race less on a sports day, it may create greater goodwill in our school community, and that itself may be more preferable in some way. But let's stay away from those complications for the time being. We've assigned values to our outcomes, but notice that because our action determines our outcome, then really what we want is to choose between actions. So what we really want is not so much this little v, which is our preferences over the outcomes, but we want some way to assign a value to an action itself. Notice, and this is important, that the little v is an assignment of a value to an outcome, or to each outcome. We're going to introduce now this big V, which is a value assignment to an action. And when we have certainty, that becomes fairly straightforward because the action determines the outcome. The outcome is determined by the action, so we might as well assign the value to the action to be the value to the outcome. Right? So little v is what we had before, which is a value assigned to an outcome by an agent, the decision maker. Big V is now the value assigned to the action by the decision maker. And we can just directly give the value of the outcome to the action, because in a situation where we're under certainty and the action determines the outcome, the two are going to be the same. Or we might as well assign one to the other. Now, a little while ago we talked about rational decision making and decision rules, or rules for making rational decisions. So now we're in a better position to describe what that means. And the idea of making a rational decision is to never choose something which is not our most preferred. Right? So we're going to introduce a principle of rationality, which we'll call the elimination principle, which is that if we're faced with multiple possible alternatives or actions, rationally, we should never choose an action which is less preferred than another one. Right? So if we're given two alternatives, we should never choose the least preferred of the two. What that amounts to, in more precise terms, is that if we're assigning, say, a value to two actions, and ultimately what we're trying to do is choose between actions, so this is where this big V function comes in. This is the assignment of a value to an action. If we're choosing between two actions, A and B, and we give B a value less than A, in other words, we prefer B less than we prefer A, we shouldn't choose A. So in terms of our previous example, the fundraiser problem, where we can choose between a sports day and a fete, if the value of the sports day is less than the value of the fete, we can eliminate the sports day because it's less preferred than a fete. There is a more preferred action, and that allows us, that's enough to justify eliminating the sports day. Now, in general, that means that if we look down here in this bottom corner, that a rational agent, a rational decision maker, if we're making decisions, if we're rational in how we go about making decisions, we should never choose any action for which there is an alternative action that gives us a more preferred outcome. In terms of these big V values, we should never choose any action S for which there is an action F which has a higher value, where that value measures our preferences. Okay, so this wraps up this section of the course. So you should now have enough information to work on most of, if not all of, the first exercise set 1. So just recapping what we did, we looked at, introduced the idea of a decision problem, a situation in which we have to make a decision. We're trying to make the best decision we can. We framed a decision problem in terms of some basic elements, right? So actions, states of the world, possible states of the world, and outcomes. Then we assemble these together, these elements together, to give some structure to our problems, to represent the decision problem, either as a tree or as a table. We introduced things like preference information and uncertainty information. Uncertainty has to do with our epistemic state, or our state of information, or our beliefs. And preference values express how we feel about outcomes, which outcomes we prefer over others. And we talked about assigning values to this. We'll look at this, at how we go about doing this in more detail later. Then we went on to talk about decision classes, and we looked at the first and simplest decision class, which is the class of decision problems in which there is no uncertainty. In other words, decisions under certainty, where the actions directly determine the outcomes, and therefore once we know our preferences over outcomes, we can translate that to make into preferences over our actions.